Hi everyone, welcome to the video. Today we're going to have a look at Introduction to Matrices. So this is from Chapter 8. Now I hope you've had a look at the quick little introduction video that I've posted online. So to start with, a definition for matrices. So a matrix is basically a rectangular array of numbers, and the numbers are arranged in rows and columns. So I've got a bit of an example here. So we've got A is the matrix 2, 3, minus 1, 1, 0, 4. So this is what a matrix looks like. Now we can say the number of rows for a matrix. So we've got 1, 2, 3 rows. So number of rows is, when my pen works, 3. So we've got 3 rows. How many columns? So there's 1, 2. So our matrix A is we say 3 by 2 matrix. 3 rows, 2 columns. It's always rows by columns. So 3 by 2. Another quick example, if we had 1, 2, 3, 4, this matrix, so this would be B, for example. So B would be a 2 by 2, because it's got 2 rows, 2 columns. And maybe we might have this one, 1, 3, 8, 2, 6, and 5. Just a random one. And this could be C. Alright, so matrix C would be it's got 2 rows and 3 columns. So that'll be 2 by 3. So this is called the order of a matrix. So this one, this, and this, they're all called order, or matrix order. So it's always rows by columns. So in general, a matrix with m rows and n columns is known as a m by n matrix. So that's a bit of a summary of what I've just shown. Okay, always rows by columns. Elements. So inside a matrix, every number is referred to as an element. So in general, the elements of matrix A are referred to as this I, J. So my matrix A before was 2, 3, minus 1, 1, 0, 4. So all these inside here are elements, is what we say. What this is talking about is where I refers to the row position and J refers to the column. So if I wanted to work out what that was, it would be matrix A, first row, first column. So the position 2 would be matrix A, first row, first column, with a comma. This one here at 1, so 1 would be matrix A, second row, second column, with a comma between them. Okay, so A, 1, 1, row 1, column 1 is 2. So this is my element. So my element A, 1, 1 is 2. So this is kind of summarising what I was saying before. So A, 1, 2 would be row 1, column 2, so that would be 3. So these are all elements. If I had A, 2, 1, so row 2, column 1, that would be minus 1. 2, 2, as I said before, so row 2, column 2 will be 1. Again, always rows by columns. And we'll have 3, 1 is 0. Third row, first column. And A, 3, 2, so third row, second column is equal to 4. So these numbers are all my elements of matrix A. So summarising, for any matrix, doesn't matter how big or how small, we can start to make a bit of a summary. So this position here, this element here, is always going to be 1, 1. Matrix A, first row, first column. This one here, second row, first column, it's always going to be A2, 1. That's the element, that's the position of element, that one. Same thing for this one. So in here, I can start to fill it out. So second row, second column. Okay, over here, second row, third column. And I can keep going. Down here, I'd have third row, second column. Third row, third column. Alright, and that pattern continues all the way down. Now the last position, all along here, and all along here. Remember our matrix is always an M by N, so rows by columns. So this position here is the very last row, which is M. So that's got to be M. So if so in this case, I don't know how big the matrix is, but I know that last position there is going to be element AM, and its column is always going to be 1 for that element. So the next one would be the same row, which is M, and it's going to be the second column. And pattern again continues, so M3, so M row, third column. Now I can start doing it on the side here as well. So this position here is going to be the very last column, which is N. And I already know that it's the first row, so it's going to be row 1, column N. And this one, second row, column N. Third row, column N. And that continues as well. And the very last one down here is going to be the M row and the N column. So A, M row, N column. Okay, so a bit of a summary. So I might have a 6 by 6. So this is the 6th row, first column, 6th row, second column, etc. This one would be the first row, 6th column, second row, 6th column, etc. And this last one down here would be the M, which is 6, the 6th row, 6th column. So that's just talking about elements of the matrix, and that's just a bit of a summary. So that's looking at where each position is. Moving on. So we've got special types of matrices. The first one is a row matrix. So a row matrix, I might say A is, and it'll probably look something like this. The elements will be different, but the row matrix is just a matrix that just has rows. Okay, it's got one row, sorry. Okay, so you got one row, 3 columns. So that would be a 1 by 3 matrix, but it's a row matrix because we've only got one row. And the column would be the same, except we're going down the page. So that could be matrix B. Okay, we've got 3 rows but 1 column. So 3 by 1. Okay, going down the page. Rows and column. Alright. A square matrix up to C, so let's go 6, 8, 10, 12. Okay, this is an example of a square matrix because, well, it's basically a square. So you've got, this one is a 2 by 2, so it means both the rows and the columns are the same. So we've got 2 rows, 2 columns. Okay, I could have a 3 by 3. Okay, doesn't matter what numbers I've got. This is matrix D. Alright, so I've got 3 rows, 3 columns, so this is a square matrix as well. So there are examples of 3 square matrices, and it can be as big as we want. So it could be 6 by 6, 8 by 8, etc. Now, a diagonal matrix is a matrix with basically numbers along the diagonal. So it could be 1, 5, 8, and the rest of the numbers are all zeros. So that's an example of a diagonal matrix. Again, diagonal matrix has to be a square matrix. Alright, so it's just numbers along the diagonal, all the rest are filled out with zeros. And doesn't have to be a 3 by 3, it could be a 2 by 2, 4 by 4, etc. It just has to be a square matrix. So that's the definition of a diagonal. A zero matrix, go back. A zero matrix, as the name suggests, is just a matrix with all zeros. Okay, it could be those as an example. So this one doesn't have to be a square matrix, it's just a matrix with all zeros in it. Symmetrical matrix, as the name kind of suggests again, is a matrix where we've got symmetrical down the diagonal. So up to F, I could have 1, 3, 8, 6, 7, and 9. Now these elements in here, that has to be a 3, because we've got a, just imagine a mirror going down that, and that has to be in 8, and that one has to be in 9. So that's an example of a symmetrical matrix. And last one, triangular. So there's 2 cases for a triangular matrix. The first one is a lower case and there's an upper case. So for a lower case, or lower triangular matrix, all the elements above the diagonal are 0. So again, we've got a diagonal, and could be some other numbers in here, but all these numbers above the diagonal has to be 0. Again, it doesn't have to be a 3 by 3, but it does have to be a square matrix. So it could be 4 by 4, 6 by 6, etc. And an upper is basically the opposite. So all the zeros are below the diagonal. So we've got zeros below the diagonal, all the rest it doesn't really matter. So that's an example of an upper triangular matrix. So we can use matrices in situations where we have a table, as the example here. So we've got a table, and instead of writing out 10 A, B, C all the time, and when we need to do calculations, it's easier if we make matrices. So I can transform this into a matrix as such. So it's just imagine you've got on the left-hand side, we've got town A, B, and C. And up the top is town A, B, and C. Well, inside town A, is going to be this 0 here. Town B, town A, 23, 17, so we can fill it out. And it's basically the table represented in a matrix. So really, we're saving a bit of time by not writing out those things, and that's our matrix. So we've got distance between 3 local townships. I'm converting it into a matrix, and that's what it would look like. Similar case here. So a different example, but we're looking at attitudes for primary and secondary students, I guess. So we can draw our matrix, and without having to write down all the information, we can say, well, the first element is going to be primary schools for fewer. Okay, so 5. And then 2 for secondary students, and then just fill it out. So 29, 9, 33, 36, 67, and 47. And we can use matrices, although we don't do a lot with this. So simultaneous equations we can use as a way to solve using matrices. So we look at the elements in front of the x and y. So we've got 3, 2, 2, and -6. And basically make a matrix around it. So just take the elements in front of the unknown coefficients, 3, 2, 2, and -6. Alright, and we will be looking at examples like this later on, but this is just as an introduction. We've got x and y, that's our missing coefficients, and that's equal to, and we'll make this as a matrix by itself, so 5 and 2. Alright, so instead of having to do this algebraically, we've got a different method, although still algebraically method, for solving. We can use matrices to solve for x and y. And in a later chapter, we'll look at how to do that. So that's chapter 8.2. In the next video, I'll go through some examples. So thank you.